So today I'm going to be explaining how to find the change in height, the change in liquid level height, the temperature of the liquid, and the concentration of A inside of the liquid inside of a tank that has 3 streams going into it. So we can draw our tank. We also know that there's a mixer inside of this tank, and it's a very good mixer because we know that our temperature is exactly the same all throughout the tank, including the flow going out, and our concentration of A is the same all throughout the tank, including the flow going out. So we have 3 streams that are coming in. We'll call this 1, 2, and 3. We also know that there is some liquid level height inside of this tank that we're going to call H, and that there is some cross-sectional area at the top, and we're going to call this AC. And then we know that there's a flow coming out of the tank, we're going to call this Q out, and that there's a hole at the bottom of the tank that the flow is coming out of, so we're going to call this AB, since it's our cross-sectional area at the bottom of the tank. And now we need to find the change in height over the change in time, the change in the concentration of A over the change in time, and the change in temperature over the change in time. So to do this, we need to find a mass balance for each of these. So let's start with the change in height. So we know that our density is the same all throughout the tank, including the flow going out, since it's a very well mixed tank. So we're going to say that our change in volume over our change in time, and we can set this equal to all of our flows coming into the tank minus our flow going out of the tank. So we can say that our Q1 plus Q2 plus Q3 minus Q out. So now we can actually write this section of this equation as the summation from I is equal to 1 to 3 of Qi, since it's just all of our initial flows in. So now we know that our volume is equal to our cross-sectional area times our height, so we can write our cross-sectional area out front, since we know that this does not change with time, it's the same all throughout the tank, times our change in height over our change in time is equal to the summation from I is equal to 1 to 3 of Qi minus Q out. Now we want to isolate our dH/dt variable, so we're going to write dH/dt is equal to the summation from I is equal to 1 to 3 of Qi minus Q out, all divided by our cross-sectional area. So that is our dH/dt. Now we can find the mass balance for our component A. So we can say that the concentration of A, we're trying to find the concentration of A inside of our tank, so we can say that we have to say that the concentration of A times volume, so we have to do dV/Ca over dt, and this is going to be equal to all of our flows in times our concentrations in. So we're going to have Q1 times Ca1 plus Q2 times Ca2 plus Q3 times Ca3 minus our Q out times our Ca. So like I said earlier, this tank is very well mixed, so we know that our concentration of A is the same going out as it is anywhere inside of the tank. That's why we can just call that Ca. So we can actually write the first 3 components of this equation too as the summation from I is equal to 1 to 3 of Qi times Cai, since it's just all of our initial flows in and our concentrations in. So now, like we did over here, we know that our volume is AC times the height, so we can write AC times dHCa, since we know that our cross-sectional area does not change, over dt is equal to the summation of I is equal to 1 to 3 of Qi CAI minus Q out times CA. So now we want to get CA, the dCA over dt by itself, so we have to do the product rule to find this. So we can say that, and we need to move AC over to our other side, so we can say that CA times the change in height over the change in time plus the height times the change in concentration over the change in time is equal to the summation from I is equal to 1 to 3 of Qi CAI minus Q out CA divided by our cross-sectional area. So now we just have to get dCA over dt on one side by itself. So we can say that our dCA over dt is equal to, so we're going to subtract this term over and then we're going to divide by h. So we're going to have the summation from I is equal to 1 to 3 of Qi CAI minus Q out CA divided by our cross-sectional area minus our CA times dH over dt, and then all of this is divided by h. So now we find our cross-sectional area, and we do see that we have dH over dt in our equation, but we're going to be able to solve for dH over dt first, and then we can just plug this value in for dH over dt. So now we have our dCA over dt. So now we just need to find our change in temperature over our change in time. So we can relate this to the energy of our system. So we are trying to find the total energy in our system, which is going to be the energy going in minus the energy going out. So we can start off with our temperature, and we know that this is in degrees Celsius. And we know that we can convert our temperature into energy by multiplying by the heat capacity, so we're going to call that CP. And this is in units of joules per gram degrees Celsius. So now we are trying to find the volume of energy inside of our system, so we need to multiply this by volume. And we know its units are meters cubed. So now if we look at our units, we know that they're not going to cancel correctly. So we also need to multiply this by our density, which its units are kilograms per meter cubed. So now, again, looking at our units, we can see that we have kilograms and then we have grams. So we are actually going to turn our heat capacity into kilograms. So it's going to be joules per kilogram times degrees Celsius. And all that we'll have to do for that is multiply our heat capacity value by 1,000. So all of that is going to be the left-hand side of our equation. So we can say that our change in density times our volume times our heat capacity times our temperature over the change in time. So now we need to look at the right-hand side of our equation, and we can say that this is our density times our heat capacity times our temperature. So again, looking at units, we know that temperature is in degrees Celsius, our heat capacity is in joules per kilogram degrees Celsius, and that our density is in kilograms per meter cubed. So now we can see that our units for this would be joules per meter cubed, which is not what we're looking for. But we know that if we multiply by our flow rate, which is in meters cubed per second, that we are going to get joules per second, and that is what we're looking for. So now we can write that we're actually going to use the summation like we did in the other two problems. So we're going to say that our summation from I is equal to 1 to 3 of our density, our heat capacity, our temperature in, our Ti, let's keep it similar to the other ones, times our Qi minus our density times our heat capacity times our T. So again, just like we did for where was it? Our CA, we know that our tank is very well mixed. So we can just say that our temperature is just T. We don't have to put T out because we know that the temperature going out is the same anywhere throughout the tank. So it's going to be T times our Q out. So now we know that our density and our heat capacity is going to be the same all throughout the system. So that's a constant. So we can technically pull the density and the heat capacity out of this derivative. So we're going to pull those out, and then we're going to divide by them. So all of the density and the heat capacities cancel throughout this problem. So this is going to leave us with the change in volume times the change in temperature over the change in time is equal to the summation from I is equal to 1 to 3 of Ti Qi minus TQ out. So now we also know that our volume is our cross-sectional area times our height. So we can change that for volume. So we're going to pull AC out front since we know it's a constant. So we're going to have dHT. So it's the change in height and the change in temperature over the change in time is equal to the same right-hand side. So it's the summation from I is equal to 1 to 3 of Ti Qi minus TQ out. So now we're going to use the product rule again to separate our derivatives. And we can also divide by AC on the other side. So we can have that H times dt, or the change in temperature over the change in time, plus the temperature times the change in height over the change in time is equal to the summation from I is equal to 1 to 3 of Ti Qi minus TQ out, all divided by the cross-sectional area. So now we want to get the left-hand side to just be the change in time, or the change in temperature over the change in time. So we're going to subtract this one over, and then we're going to divide all of it by H, just like we did for the concentration. So we're going to have our change in temperature over our change in time is equal to the summation from I is equal to 1 to 3 of Ti Qi minus RT times Q out, divided by the cross-sectional area, and then we are going to subtract temperature times the change in height over the change in time. Then we're going to divide all of this by our height. So we can actually see that our change in temperature over time and our change in concentration over time are very similar, except in concentration you're multiplying by the concentration, and in the temperature you're multiplying by the temperature. So now we have solved for the change in temperature over the change in time, and now we are ready to start coding this in Colab. Okay, so to start our code, we are going to import NumPy, Plotly, and our SciPy for solve IVP, and our SciPy for our root solver. And now we need to initialize all of our starting values for our variables that we were given in our problem statement. So we're going to start with our temperature, and we're going to do T0 since it's our initial values for the system. So our T0 needs to be numpy.array. Since we have 3 values, we need to put these in an array. So it's 80, 65, and 90. And the units of this is in degrees Celsius. And then our concentration naught is going to be equal to the same thing. We need to have an array of 0, 1, and 0.5. And the units of this should be in grams per liter. And then we're going to do the same thing for our flows in. And we have 0.5, 0.3, and 0.6. units of this is in meters cubed per second. Now we're ready to initialize our value for our cross-sectional area, which is 1 meter squared. And then our cross-sectional area at the bottom tank is 0.1 meters squared. And we're going to initialize our value for gravity. So gravity is 9.81 meters squared per second, I believe. Okay, so now we are ready to define the right-hand side of our equation. So we're going to say define right-hand side, and we are going to do our independent variable. And then we need to follow this by a vector of our dependent variables. We also need to have our flow in, our CA in, and our temperature in. We don't want to use our Q naught, CA naught, or temperature naught because these could change over time as our streams in change. And then we need to initialize a value for our vector. So we have our height, our concentration, and our temperature. And now we need to initialize a value for our Q out. So our Q out is the cross-sectional area at the bottom times the square root of 2 times G times H, and then square root. Now we are ready to enter all of the equations, all the differential equations that we just found on the board. So we're going to start out with dH/dt, which is the sum of our Q in minus our Q out. Now let's do our concentration. Our dCA dt is going to be equal to the summation of Qn times Can minus our Q out times AC or Ca. And then all of this is going to be divided by our cross-sectional area. And then we are going to subtract our concentration times dH/dt. And then all of this is going to be divided by our height. Now we need to enter our equation for our dt/dt, which is going to be almost exactly the same as our concentration. So we're going to have np.sum of our Qn times our Tn minus our Q out times our T. All of this is divided by our cross-sectional area, and then we are going to subtract our temperature times dH/dt. And then all of this is divided by our height also. Now we need to return the value of our right-hand side, so we need to have this in an array since we have 3 equations of our dH/dt, our dCA dt, and our dt/dt. So now we are ready to find the roots of our equations. So all that the root means is when the equation is equal to 0, so that would be our initial steady state. So we are going to do root of lambda, and then our vector. And now we are going to do our right-hand side. So we have our time, which we know that none of our equations depend on time. So we can choose anything, so we're going to choose 0, and then we have our vector, and our Q naught, our CA naught, and our T naught. And then we also need to define what our vector is, so we are going to say, or we're going to have guesses for all of our initial values. So we are going to use, so height we can actually find the actual value for it by flipping around the Q out equation. So we can have our sum of our Qn divided by our cross-sectional area. We got a yellow line there. We'll figure that out in a second. By our cross-sectional area squared. And then this will be divided by 2 divided by g. Oh, I'm missing a parenthesis here. Divided by 2 divided by g. And then we also need to make a guess for our concentration and for our temperature. So we're gonna look at our initial values and make our best estimated guess. So for concentration, we are going to guess 0.5. And for our temperature, we'll guess around 70. Qn is not defined. Oh, this should be our Qn not. Okay, so now we can see that our x is what the x values are what we're looking for. So this is our height, this is our concentration, and then this would be our temperature. So we are going to set our root solver equal to sol, and then if we just do sol.x, we can only pull our values that we want to look at. So from this problem, we can see that our initial height of our steady state system is around 10 meters. Our initial concentration is around 0.43 grams per liter. And then our initial temperature is around 81 degrees Celsius.